Hi everybody, welcome to the channel, or welcome back to the channel. In this video we're going to look at the second part of the Fundamental Theorem of Calculus. In the last video we proved part 1. I will say this proof of part 2 is not going to be quite as long and as complicated as the proof of part 1. It's going to be a little bit more straightforward, but the result or what it means for us in our example problems is going to be just as important. So this is going to be still something that's a really important deal for us. And when you put both of these parts together, part 1 and part 2, those collectively make up what we would call the Fundamental Theorem of Calculus. So this can be a little confusing sometimes, because when people talk about the Fundamental Theorem of Calculus, my thought in my mind is usually, well, you're talking about part 1, part 2, the whole thing, kind of what part are we talking about? So usually people, when we talk about the Fundamental Theorem of Calculus, are kind of talking about the whole thing collectively together and its implications as far as derivatives and integrals, but we need both pieces to kind of work together. So we have the statement up above. Let's go ahead and jump in. It says if f is a continuous function on the closed interval from a to b, that should sound really familiar. We've seen that opening statement quite a bit now. Then we have this result, and this is pretty great, where we have the integral from a to b of f of x, and remember the integral means the area under the curve, is equal to the antiderivative, that's what capital letter F is, the antiderivative of little letter f evaluated at b, so plug in b, and then plug in a, and subtract. In the last video I told us that the implication from the Fundamental Theorem part 1 is that an antiderivative is basically the same thing as an integral now. And this result gives us not just that they're the same thing, but there's a really nice way to be able to calculate the area under the curve by taking an antiderivative and then just plugging in the bounds, the upper bound and then the lower bound, and subtracting. Okay, so why does this work? Let's go ahead and take a look at this. Remember from the last example, we actually had a function little g of x, which we called the integral from a to x of f of t dt. And if you remember, one of the things that kind of came as a result from this was the fact that g prime of x is equal to f of x. Okay, and so what we said that means is basically that g of x is an antiderivative of little f, and here in this part 2 we're also told that capital letter F is also an antiderivative of little f. So basically g and capital letter F are both antiderivatives of little letter f. Okay, both antiderivatives of little letter f. And so basically another way to say this is to say that g prime equals capital letter F prime. Now, let's be careful. This does not necessarily mean that little g and capital F are exactly the same function. They just both have the same derivative. So we've actually seen a situation like this before in our past. And so if they are if g prime and capital F prime are equal, it doesn't mean g and f are equal, g and capital letter F, but what it does mean is that capital letter F and g are off by just a constant. Okay, so I'm going to write it like this. Capital letter F of x is equal to g of x plus c. Okay, because when you take the derivative of both sides, the derivative of the constant c is just 0, so you do get the same thing. So they're not necessarily the same function, but they're off by what we call a constant of integration, that plus c value in there. Okay, now what we're going to look at is, if you look at the result up here, on the right side of the equation, it talks about capital letter F of b minus capital letter F of a. And so we're going to kind of look at f of b minus f of a and just see if we can kind of see what is that equal to, based on knowing that capital letter F is equal to g of x plus c. So let's just look at capital letter F of b minus capital letter F of a and see what we can come up with. All right, so if we use the equation that we have up above and replace the f's with g's, here's what we get. F of b is actually looks like g of b plus c, and then minus, let's see, when you plug in f of a, this looks like g of a plus c as well. So here's kind of your f of b, and here's your f of a. Okay, now hopefully pretty easily we can see what's going to happen here with the c's at least. If we go ahead and distribute the negative and combine some stuff, we're going to end up with something like g of b, let's see, plus c, and then we're going to have a minus c, so those actually are going to cancel each other out, and then minus g of a. Okay, now you might say, well, this is a lot of f's and g's. What on earth are we talking about here? Well, remember what g is. Let's go back to where g came from. Remember, g of x is talking about this integral right here. That was the same g of x that we used back in the Fundamental Theorem of Calculus Part 1. So let's go ahead and replace the g functions over here with what g is equal to. This is the integral from a up to x, but remember, we're plugging in a b for x, so this is the integral from a to b of f of t dt, and then minus the integral from a to, let's see, we're replacing an x with an a this time up here, of f of t dt. Now this one actually should work out fairly nicely because you might remember what happens when you have the integral from a to a. Remember, the picture that we have basically says start at an x value of a, or in this case a t value of a, and go up to a t value, well, I guess it would be an x value here. Start at a and go to a, okay? And so this is basically just 0. And so what we end up getting is something like this that says capital letter f of b minus f of a. If we just kind of look at what this is equal to, now what we have is that this is equal to the integral from a to b of f of t dt. Now, I will point this out. Remember that earlier in part 1, we were using t right here because we were using x as our bounds. We had an x up here earlier. Okay, that's why we were using t, but t was just another way to call our input variable. We just used a different labeling. And so now, in this problem, at this point now, there's no more x up in the bounds. Okay, b is now a constant up here, and because both a and b are constants, and those are the endpoints of your intervals, we no longer have an x as the bound up here. We don't really need to call this t anymore in here. Now we can call it x like we have been, and so, or like we want to, I should say. And so really this is the integral from a to b of f of x dx, as we relabel to have our input variable be something we're a little bit more familiar with. So the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. Okay. Now, we're going to see let's just look at one example of why this is meaningful. By the way, that's the end of the proof. We're done. Cool. Awesome. That's exactly what we wanted. So let's go ahead and take a look at an example of why this is useful. Okay, let's say we have a function that, if you remember talking about the areas of area under a curve back in a couple of videos ago in the last section in the book, we had something like f of x equals x squared, and we could look at the area from x equals 1 to, I don't know, x equals 3, for example. So here's kind of the picture of this. The picture looks like your normal quadratic function, and basically saying from x equals 1 to x equals 3, find the area under this curve. Okay, so the best that we were able to do back in the last section, if you remember, I made a video about how to use rectangles. Do you remember using rectangles and talking about left-hand sum and right-hand sum? And that was kind of the best that we could do, was use rectangles to try to find, to try to estimate the area under the curve. And we were never going to be exact using rectangles unless we could somehow use infinitely many rectangles. And that kind of gave us the definition of the definite integral. But we can't really use infinitely many rectangles by drawing a picture, and we can't get an exact value by just coming up with a left-hand sum or a right-hand sum. And even when we could, use a lot of different rectangles to have a closer and closer approximation, that was a hard problem to work with, and that took a lot of time and a lot of effort. Okay, but now that we have the fundamental theorem of calculus to find the exact area under the curve, which is the integral from x equals 1 to x equals 3 of f of x, which is x squared, dx, we don't need to use left-hand sums or right-hand sums anymore. Now all we need to know, and this is the application from the fundamental theorem, all we need to know is that, oh yeah, when we see an integral, that just means the same thing as an antiderivative. Okay, so we should be able to look at this and say, can I take the antiderivative of x squared? Well, that's a power rule, and so kind of think about going back up in the other order. This would be an x to the third power, going back up the power rule. But then remember, you need a number down in front that's going to cancel out the 3 that drops down from the power rule, so you need a 1/3 there. And here's the notation that we use with this definite integral when we're using this fundamental theorem of calculus. We would say, here's the antiderivative, but then we're also going to put this little vertical bar here that says start at x equals 1 and go up to x equals 3. And basically, that's just a reminder for you, first of all, of what the input variable is. The input variable here is x, but it also tells you what b is and what a is, to go ahead and plug those in, because remember, the result says go ahead and just take f of b, f of a, and basically once you have your antiderivative, just plug in those endpoint values and subtract, and you'll be able to find the exact area under the curve. So the exact area under this curve from 1 to 3 is 1/3 times 3 to the third minus 1/3 times 1 to the third. Okay, now we could try left-hand sums and right-hand sums, and we would get some kind of decimal value, and we'd say, oh, we're close, and we can get even closer by averaging, but we can get an exact area now under the curve here with these. And again, that uses the fundamental theorem. Go ahead and simplify this. 3 to the third is 27, so 27 divided by 3, you get 9. And then minus 1/3, you actually end up getting, let's see, what would that be, 27 over 3. So you end up getting something like 26 over 3 if you want it as a fraction, or that's 8 2/3 as a mixed number. Okay, so there's your exact value, not an estimate, not an approximate, for the area under that curve. And again, that uses the fundamental theorem of calculus. Okay, in the next section in the book, there's actually not going to be a ton of stuff new. It's going to be a lot of practical applications or specific examples using this fundamental theorem that says take an antiderivative, and then if you have a definite integral where you have a lower bound and an upper bound here on your integral, then don't forget to plug in b and plug in a after you take the antiderivative and subtract and get a specific value as your answer. Okay, so here's the fundamental theorem part 2, along with the proof of that, as well as an example problem showing how that's useful. Okay, hope you've enjoyed.